Discuss some problem related to chapter number 10. The first problem 10.1 show that the differential equation for V and A, scalar potential and vector potential, this equation, and we have given this equation. This is equation 1 and this is equation number 2. Can be written in more symmetrical form. These two equations, equation 1 and equation 2, can be written in more symmetrical form like this and this, where L is given divergence of A plus mu naught epsilon naught partial V divided by partial T, and where this D'Alembert, which is equal to, this is an operator, space-time, depend upon space and time. So del square minus mu naught epsilon naught partial square divided by partial T square. So the simple thing is we have to written these two equations in these two forms. So first of all, I want to consider equation 1 solution. I want to consider this equation del square plus partial divided by partial T divergence of A, which is equal to minus rho divided by epsilon naught. I think this is epsilon naught. Now we need for this divergence of A, and this divergence of A can be obtained from this relation. So from this relation, divergence of A, which is equal to L minus mu naught epsilon naught partial V divided by partial T. So del square V plus partial square divided by partial T square, and the value of divergence of A will be equal to L minus mu naught epsilon naught partial V divided by partial T, which is equal to minus rho divided by epsilon naught. Multiply this partial square divided by partial T square, then we have del square V plus partial square L divided by partial T square minus mu naught one thing I have written, this is not partial square, this is not a partial square, this is a partial divided by partial T, so this is a mistake. Partial divided by partial T, so partial divided by partial T, mu naught epsilon naught, and here partial square V divided by partial T square, which is equal to minus rho divided by epsilon naught. Now from here and here we can take V common, del square minus mu naught epsilon naught partial square divided by partial T square. So we have common V plus partial L divided by partial T, which is equal to minus rho divided by epsilon naught. And this term, we have given this term, this is equal to the D'Alembert, and this is D'Alembert square V plus partial L divided by partial T, which is equal to minus rho divided by epsilon naught. So this is the required result. Now the second part, this equation. Consider equation number 2, del square minus mu naught epsilon naught partial square A divided by partial T square minus del into divergence of A plus mu naught epsilon naught partial V divided by partial T, which is equal to minus mu naught J. This term, this is equal to L. So putting the value, del square minus mu naught epsilon naught partial square uh, we must have partial square A here. Yes, this is a partial square A. Divided by partial t square minus del into L, which is equal to minus mu naught J, and take common from A from these two terms, then del square minus mu naught epsilon naught partial square divided by partial t square, and A minus del L minus mu naught J. And once again, this is equal to d D'Alembert square A minus del L, which is equal to minus mu naught J. So this is the required symmetric this form. This is problem number 10.3, and according to this problem, find the fields, electric field and magnetic field, and the charge and current distribution corresponding to V of RT is equal to 0 and A, which is equal to this. Then use the gauge transformation, gauge function lambda is equal to this to transform the potentials and comment on the result. So first of all, we need to calculate the electric field and magnetic field. Electric field and magnetic field. We know the electric field as minus del V minus partial A divided by partial T. And here V is equal to 0, so this term is equal to 0 minus partial divided by partial T, and A minus 1 over 4 pi epsilon naught QT divided by R square, and R is a unit vector. If we differentiate this with respect to T, then partial T divided by partial T, this is 1, and we have only minus 1 over 4 pi epsilon naught Q divided by R square, and R as a unit vector. So this field, this is just like a charge, this is just like a field, just like a field that can be generated due to a point charge. At the origin. If the charge, just like a point charge, and it is situated on the origin, then it means that for this charge, the vector potential goes to 0. It means that A, which is equal to 0. And when A is equal to 0, it means that del cross A, which is equal to B, the magnetic field. If A is equal to 0, then it means that magnetic field is also equal to 0. So this is the electric field that we have find out, and this is the magnetic field, which is equal to 0. Further in this question, we are also asked to find out the charge density and the current density as well. To find the charge density, we must charge per unit volume. We have this kind of relation. And charge per unit volume for a point charge, this is approximately equal to Q and delta cube of R. So this is the charge density, and where the current density, current per unit area. So this is a point charge, there is no current, then the current is equal to 0, then J will also equal to 0. Solution of B. As we know that by the gauge transformation, V prime, which is equal to V minus partial lambda divided by partial t. And here the gauge function is given, lambda is given, V prime, which is equal to, this is equal to 0, and partial divided by partial t, and lambda minus 1 over 4 pi epsilon naught qt divided by r. And V prime, which is equal to minus minus plus, and partial t divided by partial t 1, then 1 over 4 pi epsilon naught q divided by r. So this is the potential of a point charge. And similarly, the vector potential A prime, which is equal to A plus delta lambda. This is the gauge transformation for scalar, and this is for the vector potential. So A prime, which is equal to, we have this A. So the value of this A minus 1 over 4 pi epsilon naught qt divided by r square, and r is a unit vector, plus delta lambda. Delta lambda, lambda is this one, minus 1 over 4 pi epsilon naught qt divided by r, and we may have r as a unit vector. And A prime, which is equal to minus 1 over 4 pi epsilon naught qt divided by r square, r as a unit vector. We have this minus and 1 over 4 pi epsilon naught qt, and gradient of 1 over r, and r is a unit vector, and gradient of 1. Now further, this A prime, which is equal to minus 1 over 4 pi epsilon naught qt divided by r square, r is a unit vector, minus 1 over 4 pi epsilon naught qt, and the gradient of 1 over r square means minus 1 over r square, and r is a unit vector. This minus multiplied with this, then the transformation of this 4 pi epsilon naught qt divided by r square, minus minus plus 1 over 4 pi epsilon naught qt divided by r square, r is a unit vector. And here this is plus and this is minus. It means A prime, which is equal to 0. This gauge function transforms the potentials into ordinary potentials of a stationary point charge. This is the count of these two potentials. This is problem 10.5. Which of the potential in example 10.1, problem 10.3 and problem 10.4 are in Coulomb gauge, which are in Lorentz gauge? Remember that in example 10.1 we have the scalar potential V is equal to 0 and vector potential which is equal to mu naught K divided by 4C and CT minus X absolute square and Z this one. So this is we can take this from example 10.1. Now the condition for Coulomb gauge is divergence of A which is equal to 0. Let's consider divergence of A. So divergence of A which is equal to, let's see, the divergence of A which is equal to mu naught K divided by 4C CT minus X square and in the Z direction. This clearly states that the divergence of this means partial divided by partial xi, partial divided by partial yj, partial divided by partial zk, and divergence of mu naught k divided by 4c into ct minus x square and z direction. So it will be more suitable if we replace x by I by x unit vector, and this is by y and this is by z. So because here in this it is being used z direction, so this is very convenient to write this in these kind of unit vectors. Now x dot z 0, y dot z 0, z dot z 1. So it means that only we can consider this term. Partial divided by partial z and mu naught k divided by 4c ct minus x whole square. And this term does not depend upon z because this is the differentiation with respect to z. So there is no z involved here. It means that this is equal to 0. If this is equal to 0, then the divergence of A, the Coulomb condition is satisfied. Right, then the divergence of A which is equal to minus mu naught epsilon naught partial V divided by partial T. This is the Lorentz gauge. If this is equal to divergence is equal to 0, then minus mu naught epsilon naught partial v divided by partial t. It means that partial v divided by partial t is also equal to 0. This term is equal to 0. This term is equal to 0. It means that Lorentz gauge is also satisfied. In problem number 3, 10.3, the potential is equal to 0, and where the vector, the scalar potential is equal to 0, where the vector potential A, which is equal to minus 1 over 4 pi epsilon naught qt divided by r. Now looking again for the Coulomb gauge, and the Coulomb gauge divergence of this, so divergence of A which is equal to minus 1 over 4 pi epsilon naught qt divided by r square. And from this, minus 1 over 4 pi epsilon naught, and also we can take qt outside, and divergence of 1 over r square. The divergence of 1 over r square, this is equal to 4 pi delta cube of r. This point is already we have proved in the previous lectures, that this term, the divergence of 1 over r square, which is equal to this, then this will cancel out, and we will have minus qt divided by epsilon and delta cube of r. This is a delta function where the divergence of A, which is equal to this, and this is not equal to 0, so these potentials does not satisfy the Coulomb gauge. Similarly, we can look for the Lorentz gauge, and for the Lorentz gauge, the divergence of A, which is equal to this, and the left hand side and the right hand side is not equal. It means that this, and for the condition for the Lorentz gauge, which is equal to minus mu naught epsilon naught partial v divided by partial t. So this is the condition for the Lorentz gauge. 1 over, okay. So already we have find out the divergence of A, which is equal to this, and potential, which is equal to 0. So this is not satisfied. The Lorentz gauge is not satisfied. So it means that both the gauges are not satisfied. In problem 10.4, the potentials are, the scalar potential is equal to 0, where the vector potential, which is equal to a naught sine of kx minus omega t, and this is in the y direction. So this is the similar case for the divergence of A, which is equal to the, if we take the divergence, partial divided by partial x partial divided by partial y partial divided by partial z dot a naught sine of kx minus omega t in the y direction. So x dot y 0, y dot 1 and z dot y is equal to 0. So it means that we have only this term partial divided by partial y and a naught sine of kx minus omega t. And here there is no any value for y, so this is constant for this. So it means that is equal to 0. And the divergence of A, which is equal to 0, it means that the Coulomb gauge is satisfied for these potentials. And similarly, if the Coulomb gauge is satisfied, then the Lorentz gauge, the divergence of A, which is equal to minus mu naught epsilon naught partial V divided by partial T. For this, the left hand side, which is equal to 0 from this, and the right hand side, we have also V is equal to 0. So 0 is equal to 0. It means that the Lorentz gauge also satisfied for these two potentials. And then in this equation, a time-dependent potential charge Q of T at the origin, which is equal to this. The charge density, which is equal to Q of T delta cube of R, is fed by a current density J, which is equal to minus 1 over 4 pi Q dot divided by R square, and R is a unit vector. Q dot means partial Q divided by partial T. Check that charge is conserved. We have to check that the charge is conserved. How is it possible and how we can prove? We can prove this by using the continuity equation. We know by the continuity equation the divergence of J, which is equal to minus partial rho divided by partial T. This is the continuity equation. We will start the divergence from the divergence of J, and to prove this equation, let's consider the divergence of J, and we know the divergence of, we know the J is equal to minus 1 over 4 pi Q dot divided by R square, and R is a unit vector, and minus 1 over 4 pi Q dot means dq divided by dt, and the divergence of 1 over R square, because the divergence is a space part, so it didn't depend upon the time, so we can take out this from this here. Now this, the divergence of 1 over R square, we already proved this point that this thing is equal to 4 pi and delta cube of R. Now this will be cancelled out, and minus d divided by dt, and q, because this depends upon time, then q of t, and delta cube of R. And this thing is nothing but this is the charge density rho. So it means that minus d rho divided by dt. So we started from this divergence and reached to this equation. So it means that the charge is conserved because this is being confirmed from this continuity equation, d rho divided by dt. Next part of this equation is find the scalar and vector potential and the Coulomb gauge. So we start from the potential The solution is V of R and T, which is equal to 1 over 4 pi epsilon naught integral of rho of R prime into T divided by R and dt prime. So we will start from this equation, the potential, and we have given that this charge density is equal to this. So this is given rho of R and T, which is equal to Q of T and delta cube of R. So if this is R prime, then this be R prime. Putting the value of this in this equation, so V of RT, which is equal to 1 over 4 pi epsilon naught, and this is equal to Q of T and delta cube of R prime dt prime divided by R. And we can take out this Q of T outside 4 pi epsilon naught and delta cube of R prime dt prime divided by R. And this integral is equal to 1 over R. This integral is equal to 1 over R, because if we have a source of charge here and we are making the potential here, so this is the source and this is R, and we have, let's suppose this is the origin, this is at a distance R, and we are looking from this origin and this is R. So from this whole scenario, we can say that the integration of this, which will be equal to 1 over R, and here Q of T divided by 4 pi epsilon naught and 1 over R. So this is the potential. This is the scalar potential. Here in this problem, this is just like a point charge, the potential like a point charge. Then the magnetic field is equal to 0. If the magnetic field is equal to 0, then the vector potential must be equal to 0. So this is the solution. Part C states that find the fields and check that they satisfy all the Maxwell's equation. So we need to find out electric field and magnetic field. So electric field, which is equal to minus del V minus partial A divided by partial T. We know that A is equal to 0, so it means that this goes to 0. Then the electric field, which is equal to minus del V, and we know the potential we know, so the gradient of this minus del V we already calculated, minus 1 over 4 pi epsilon naught Q of T divided by R. So from here, minus maybe there is no any minus, so this is plus. Okay, so minus del into this potential, and then minus Q of T divided by 4 pi epsilon naught and gradient of 1 over R. The gradient of 1 over R is minus 1 over R square. So the electric field minus q of t divided by 4 pi epsilon naught, the gradient of this minus 1 over r square, and minus minus plus, so the electric field 1 over 4 pi epsilon naught q of t divided by r square, and r is a unit vector. So this is the electric field. And the magnetic field is equal to 0 because A is equal to 0 and del cross A. So this is by definition the magnetic field is this. So del cross A is equal to 0, so the magnetic field is equal to 0. Now we have the electric field and we have the magnetic field, and we have to prove all the four Maxwell's equations.